okay, so probably I don't have to introduce who he is, but just several words. So he is currently the director of the Institute for Nuclear Theory and also a professor in the physics department at the University of Washington. And he was actually in the past permanent staff at Fermilab and also at University of Minnesota, where he invented the famous color glass condensate, and also the Brookhaven National Laboratory, where he invented the today's topics, quarkyonic matter. And so he's actually known to be the godfather who likes to name many concepts. And actually, not only a color glass condensate and quarkyonic matter, also the chiral magnetic effect is also named by him. And so today, he's telling us about quarkyonic matter that confused many people, including myself. And so I hope to have exciting discussions. So please start, Larry.
Kenji, you still don't understand quarkyonic matter? For shame. It's really wonderful to see everybody here. Wonderful to see, in particular, my Chinese friends who I haven't seen for quite some time. It's heartwarming to see everyone. It's been a very difficult time we've all gone through for the past 2 years, and hopefully we're coming out of it and we'll all be able to see one another again. Much of this talk is material which has been presented before. In the end, I'll give you a little bit of new material, but I think it's good to go over this in a systematic way because, of course, not everybody's been an aficionado of quarkyonic matter. The reason why I think it's interesting now is because quarkyonic matter has generic properties which suggests that it may be relevant for neutron stars, but it may not be. It may be just an interesting intellectual game, but it's kind of fun to think through, and people are thinking through it now in various different contexts. And I'm going to try to develop towards the end of this one framework for thinking about it. This work is done in collaboration with Rob Pisarski, Toro Kojo, Yoshimasa Hidaka, Sanjay Reddy, Kisang Zhang, Diana Duarte, and Saul Hernandez in various collaborations. Okay, as I said, the mass and radii of observed neutron stars and data from neutron star collisions give an excellent determination of the equation of state of strongly interacting matter. It'll get better. It's not perfect, but it's one of the surprising things that the best information on the equation of state of strongly interacting matter, in my opinion, now comes from neutron stars. There's good information at RHIC at high temperatures, but I think that constraints one gets from neutron stars are even stronger, and they take you into a different region, of course, of high baryon density and low temperature. People can hear me okay? Kenji, it's okay? Kenji?
Yes.
Yes, perfect.
Okay. One conclusion from the neutron star analysis at zero temperature is that the equations of state need to be hard. The sound velocity is greater than or of the order of a third at only a few times nuclear matter density. That's a quite remarkable fact because a few times nuclear matter density is not a very large change in the typical interaction length between matter. You're just squeezing the system so that this typical distance scales are maybe 40% or 50% higher, and the sound velocity squared has risen from some number between 10 to the minus 1 and 10 to the minus 2 up to a third, and perhaps exceeds it. This is not what one expects from a phase transition. If one had a first order phase transition, one would expect the sound velocity to actually go to zero for some range. If it was kind of a crossover, one would expect it to be small. Perhaps it even is small for a little while at very low densities, but certainly by the time you're at a few times nuclear matter densities, it's very hard. And that's a remarkable thing because the sound velocity of square to the order of a third suggests that relativistic degrees of freedom may be important. How does that happen? How does it happen that one is originally thinking about a gas of nucleons, which largely aren't interacting, and you squeeze it by a little bit, and all of a sudden the sound velocity squared is looking like a system which is relativistic? That's quite remarkable. And that's just an experimental fact, and it deserves an explanation. I'm not going to claim that this is the only possible explanation. There may be a variety of different explanations, but it deserves a simple and intuitive explanation of why this phenomenon occurs. Okay, after a short review, I will discuss a field theoretical method to include both quark and nucleon degrees of freedom in a consistent formalism, which avoids double counting of the nucleon and quark degrees of freedom. That'll be the content of the latter part of my talk. Okay, so let's begin. Oh, let's see what happened here. Why can't I go there? There I go up and down. Okay, it just had to pop a few times. Let's first understand the relationship between high temperature and low baryon density matter, and that at high density. It's useful to think in the limit of a large number of colors. This is, in fact, when one does the calculations at finite density, typically factors of NC enter in with some relatively large power. So this may not be such a bad thing to do to understand qualitatively what goes on. In this limit, if you compare a quark loop compared to a gluon loop, the gluon loop is always a factor NC larger than a quark loop. That's because gluons carry NC squared degrees of freedom and quarks carry NC. And you always adjust the coupling constant so that the one loop term with gluons is of order 1. And therefore, that means that the quark loop contributions are suppressed by a factor of 1 over NC. And that means in the large NC limit, quark pairs are not very relevant. And so, and they are what are responsible for well, in the vacuum, they're what are responsible for making the long-range linear potential short out. Basically, if you try to pull a quark and an antiquark a pair apart, and the distance becomes too large, the linear potential becomes so big that quark pairs occur, mesons are produced, and the potential of interaction can no longer grow. This is seen in E plus E minus annihilation, where you make jets. You don't make quarks, you make quark and antiquark pairs, and then those quark antiquark pairs move apart, and then they fragment into mesons. So in the end, no fractionally charged particles are produced. There's no linear long range force. Okay, in a large NC limit, you need to know that baryons are very heavy because they're made of NC quarks, so their mass is order NC. The other thing you need to know is that mesons are weakly interacting, largely because quarks interact much more weakly than do gluons with stuff, and their interaction strength is of order 1 over NC. You can also imagine thinking about hadrons to understand the large NC limit. Surely, when you think about finite temperature in the large NC limit, because when quarks are no longer important, you can have a linear force at large distances. So what happens at finite temperature? What happens at finite temperature is that, in fact, even though the gluons carry a fundamental, no longer carry a fundamental unit of charge, they can appear between a quark and antiquark pair, and on the average, in interval over time, or some averaging over particles in a media, the potential can get shorted out. And that's because at finite temperature, the gluons are there, they can be there, and on the average, they can cancel the effect of the long-range force. And so there's a deconfinement-confinement transition because, of course, at 0 temperature, the potential is linear to large distances. and there has to be some temperature at which that linear potential gets converted into potential, which is no longer growing at large distances. So all of that's pretty straightforward. You can think about what happens in terms of hadrons too, because mesons interact very weakly at low temperatures, and because nucleons are so massive and they aren't there, in fact.
Larry, there is a question exactly on that point. The Ian asks the question, why baryon mass scale with NC, given quark mass only contributes to the small fraction of the proton mass?
Well, there's a difference between the constituent quark mass and the current quark mass. Okay, and when you think about when you're thinking about masses at low temperatures, you should imagine that chiral symmetry has been broken and the quarks have a mass which is of order the QCD scale. And so that means mesons have masses, so typical masses of order twice the QCD scale, but nucleons have masses of order NC times the QCD scale. And it's because the masses aren't the current masses, they're the constituent masses. And you know, it would be unusual if you had chiral symmetry breaking and mesons had a mass of order several hundred MeV, and the nucleon had zero mass. Impossible to imagine, because the quarks inside the baryon are going to have some mass which is generated by chiral symmetry breaking. It's true, you have to think of that cloud of stuff surrounding the meson is made of gluons, but it certainly will happen. Okay, is that okay?
I think it is okay.
Okay, at low temperatures, they're gas of very weakly interacting hadrons, since nucleons are important. T is much less than lambda QCD. The density of mesons is of order 1 in powers of NC because they're color singlet. However, if you had a deconfined gas, you could have gluons present, and the energy density would be generically of order NC squared because they're of order NC squared degrees of freedom of gluons. Therefore, at some temperature, there has to be a dramatic change in the energy density as a function of temperature. It will change from being of order 1 in powers of NC to order NC squared. And the reason why this happens is because if you start raising the temperature for mesons, eventually you get to a Hagedorn temperature where the meson density grows and grows and grows and grows. Okay. And even though these things have cross sections which are small, when the density becomes of order NC squared, there's so many of them that even with small cross sections, the interactions are important. And those interactions, thought about in terms of mesons, are what terminate the growth. But that happens when the energy density is of order NC squared. And so there's a consistent framework of thinking about this at low temperatures as a gas of mesons converting into a gas of gluons at high temperatures. So what about finite density? How do we think about that? Okay. At finite density, there aren't any thermal gluons present. They're just not there. The only thing there, which is physical in the media, which can cut off the effects of the confining potential, are quarks. But we've already argued that quarks generically are weaker by a power of NC than gluons. Okay. So at finite temperature, the device screening mass 1 over r squared goes like g squared at 2 times t squared, where a factor of NC has been absorbed into g squared associated with the gluon loop. At finite density, the scale's no longer associated with temperature, it's associated with a quark chemical potential. That's a typical energy scale of degrees of freedom in the problem. Okay, so in the large NC limit, 1 over the radius squared of quarks goes like mu squared q over NC. So that means in the limit of NC goes to infinity, the typical radius you have to have, distance you have to have before device screening turns on, grows like NC and becomes infinite. So in the strict large NC limit, it's very difficult to imagine how the confinement transition can happen. it's moved off to a chemical potential, which in terms of dynamical scales in the system is some mu squared, which is of the order of square root of NC times the typical QCD, mu squared, which is the order NC times the typical QCD scale. So what does all this mean for the phase properties of matter? I'm showing a very busy slide here, okay? And let's look at that slide for a second. There are two axes on it. One's the temperature and one's the quark chemical potential. And let's first go down to the case where the chemical potential for quarks is small, 0. And that's the typical region of the confinement deconfinement transition. As you increase temperature where mu quark is close to 0. In the large NC limit, because in the large NC limit, there is real confinement. There's a real confinement deconfinement phase transition, which is a first order transition. There's that dashed red line, okay? And so you eventually go into deconfined quark-gluon plasma. Now in the large NC limit, I just argued that quarks don't affect the shorting out of the potential at all. So that dashed line becomes a straight line as you increase mu quark. In other words, there's some temperature for the confinement transition, which, it's just a constant temperature, no matter how high the quark density is in a large NC limit. Now, of course, that gets changed when you put in order 1 over NC corrections. And so the dashed blue line on the right, there's a dashed red line, and then there's the first blue line, and then there's a second dashed blue line. The second dashed blue line is to indicate what happens if you include the 1 over NC effects from mesons. And in that case, you see that there's a transition to a deconfined quark-gluon plasma at some temperature. But then now let's look at this, let's look in the region on the left where I've written confined mesons and very few nucleons, hadronic matter. What do I mean there? What I mean there is that there's a region, of course, at low temperatures and low densities where the degrees of freedom are confined mesons. But in the large NC limit, there's no nucleons there. Why is that the case? Well, think about the density of baryons. It goes like e to the baryon chemical potential minus the energy over T, okay? And and you see what happens if mu b is small, like mu b is 0, that goes like e to the minus energy over T. And the energy of a baryon is at least of order the nucleon mass. The temperature is a few hundred MeV. So that'll fall like the exponential at least of e to the minus baryon mass divided by T, which goes like e to the minus NC. So because the baryons are so heavy, if they go like of order NC, they're exponentially suppressed at low temperatures. So in the large NC limit, this gas of confined mesons is in fact a gas of confined mesons, and there's no nucleons there at all. Okay, but at some point, the chemical potential can become large enough so that e to mu b minus e over T can change sign. And when that happens, the baryons can come into the system and you can saturate with some Fermi gas of baryons. So there's some other region in between the left dashed blue line and the right dashed blue line where you have a gas of mesons, glue balls, whatever, because they're still confined. But you also have some baryons present, okay? And the surprising thing is that the density region in which you can have that gas of mesons and glue balls together with baryons goes from a region of quark chemical potentials, which are order lambda QCD, to this ridiculously high value of square root of NC times lambda QCD. What does that mean? Well, that scale is very, very large compared to the typical QCD scale. So you might have thought that the degrees of freedom in that region should be thought of as a gas of quarks rather than a gas of baryons, and the confining effect shouldn't be important. Yet the confinement transition is at yet even higher densities. So you have to scratch your head and think about this. What does this mean? And that's the reason why, Rob Pizarski is really the one who's responsible for this name, not me. I'll blame it on Rob. Quarkyonic matter is what this is called because it has properties which you might have thought would be associated with baryons because it's confined. Yet at the same time, the typical energy scale is very large compared to the QCD scale. And so you have to think about it in quarks. And because you're confused and you don't understand what that really means, you invent a name for it and you call it quarkyonic because the ionic comes from baryonic and the quark comes from quark. That's a useful thing for young people to know. When you don't understand something, invent a name for it. Okay, it's always good to do. Okay. So let me try to give a qualitative explanation of how this might happen. Okay. A way of thinking about this is to think about a Fermi surface. Think about it at zero temperature. And what I've drawn there, the radius of this sphere is the Fermi momentum. So I tried to draw a three-dimensional picture of a Fermi distribution. Okay. And if you're in the quarkyonic phase, the typical scale, the typical radius of that Fermi sphere is very large compared to the QCD scale. Well, if you think about interactions deep inside the Fermi sea, they're controlled by exchange interactions, and those interactions should be typically at the scale of the momentum of the quarks inside the Fermi sea. So that interaction scale is large. So the quarks inside the Fermi sea are interacting quite weakly. However, near the Fermi surface, you can have particles in the Fermi sea which scatter outside the Fermi surface. And when they scatter outside the Fermi surface, all momentum space is available. And so for things which are close to the Fermi surface, you can have long-range interactions. And so near the Fermi surface, there's presumably non-perturbative interactions are very important. And that suggests that there's some scale size associated with the Fermi surface which controls interactions and makes their interactions of order lambda QCD. Another way of thinking about that is you have the filled Fermi sphere of quarks, and on the surface, you have a Fermi surface of nucleons. But that's probably not a really complete picture either, because there's probably some kind of more or less continuous transition between the quark degrees of freedom and the nucleon degrees of freedom. So drawing in terms of red and blue is always a very naive thing to do in any sphere of an intellectual endeavor. And the other thing which is true is when you think about the Fermi sea and think about it in terms of quarks, there has to be some density at which this Fermi sea first appears. When it first appears, then you should probably think about it in terms of hadron degrees of freedom. So how do you think about that Fermi sphere then? Well, I think a way to think about it in a pretty much kind of conceptually independent way is when you go to high density, in some density region, the occupation number for all of the possible states in the system is completely full. In this case, it would be quark occupation number. But nucleons are made of quarks. So you can actually make a filled Fermi sea of quarks by picking off pieces of nucleon wave functions. Of course, the nucleon won't do it because the nucleon has only some subset of the wave functions. But if you start adding in deltas and stars and whatever, you can imagine getting into a situation where you just can't add any more stuff to the system because all the states are full. So I think of this blue region when it first forms as just some configuration of degrees of freedom where there aren't any allowed states. It's completely blocked for all hadronic states. And then there's some region near the surface where presumably there are nucleons, and those nucleons don't saturate all the quark degrees of freedom. Okay, they cannot penetrate into the sea where all the degrees of freedom are filled, because nucleons are filled with quarks. Okay, so in fact, this filled Fermi sea where all of the degrees of freedom of fermions are completely filled up repels the lightest mass states to the surface because they're lighter than the typical quarks inside the Fermi sea, and they sit on the Fermi surface. And that's a dynamical reason for having this kind of shell structure. Okay, so one should try to Ulrich, you'll be happy there's another spelling error. So let's see, one can think about this also about what happens with chiral symmetry. And that was a
Larry. So before coming to chiral symmetry, so there is another question by E. He asks a question: what stops the formation of a Cooper pair of quarks nucleons for this phase? That is a question.
You mean real Cooper pairs or baryonic Cooper condensation?
Well, so he's asking both. I mean the
Nothing stops it. You know, is near the Fermi surface. You know, you have to think of the Fermi surface. You have to think about in terms of nucleon degrees of freedom, but presumably there is some kind of Cooper pair formation near that Fermi surface for you know, things like superconductivity and color superconductivity. I don't see any objection to it. Maybe in the formal large NC limit, it there might be some problems with it, but you know, one deals.
Yes, indeed. For color superconductivity, the large NC argument is so this favors such the formation of quarks. But what about the nucleon? I mean the nucleon gap energy.
Yeah. Well, that's a very good and a very deep.
So superfluidity in turn, in other words, the superfluidity of nucleons.
This does look like a condensation phenomenon, doesn't it? Because on the Fermi surface, you have some low states which are lower than the energy of the degrees of freedom inside that Fermi sphere of fully filled states. And there probably is a way of thinking about this where the nucleons are effectively some sort of, you know, kind of bound state structure. There's probably some gap equation. It's a very good question. It's something which we tried to think about, but not entirely successfully. So there is a story there to be understood. What can I say? Okay.
Okay. Thank you.
Okay, but anyhow, Toro Kojo actually did a very interesting calculation in this intermediate region, because it looks like at first in this intermediate region where the scale size is large compared to lambda QCD, that chiral symmetry would be restored. And that would be a strange situation where chiral symmetry was restored before you had deconfinement, and that would violate your understanding at least of what happens at zero quark chemical potential, and many dynamical models would have problems with it. And what Toro actually showed was very interesting. He showed that, in fact, in this intermediate region, chiral symmetry is broken in a translationally non-invariant way. And this led to some work in NJL models where they found that, in fact, there is some intermediate region which can exist where chiral symmetry is broken in a translationally non-invariant way. And so presumably this region, quarkyonic matter, is very rich in its structure. I agree, there are issues of superconductivity there, which need to, or condensation, which need to be understood, both for baryons and also in terms of how chiral symmetry is realized. So, you know, if I could present everything as being understood, it wouldn't be so interesting, but there's clearly something very interesting in this region of quarkyonic matter to be understood. Okay, so there's some simple large NC considerations which you should understand about how this works. Okay, yeah, one of the remarkable things about nuclear matter is that the Fermi momentum scale in real nuclear matter is of order lambda QCD, beyond several hundred MeV. Okay, and if you ask what that means for the typical energy per nucleon, okay, that means the typical energy per nucleon is lambda squared QCD over 2mn, and that's of order lambda QCD over NC. So the energy per nucleon in nuclear matter is very, very small. On the other hand, the short distance QCD interactions are of order NC, and the energy per baryon there should be of order NC times lambda QCD. That's quite remarkable that the energy density of nuclear matter, the energy per particle of nuclear matter will change from something of order 1 over NC to something of order NC. Notice that this is happening at a density of hard cores, which is parametrically of order lambda cube QCD. So this suggests that somehow that the degrees of freedom of the system, the energy per particle changes very, very rapidly in some kind of narrow range of densities. Here's a very nice plot which was done by Kenji, and there's also work which was done by Carlson, Gandolfi, and Reddy, Kojo, Anala, Goda Kurkula, and the Japanese group. A whole number of people have contributed to this. But I'm just showing this plot because it's kind of a nice one. It's a plot which is constrained by data and doing kind of a numerical analysis to determine what the sound velocity squared is, which is required at various equations of state to explain the mass radius relation. You see, to get a mass radius relation from a neutron star, all you do is solve the equations of hydrostatic equilibrium. And that requires knowing a relation between the pressure and energy density. Well, if you then try many relations between pressure and energy densities, you will find only a few which fit the data. And this is an attempt to realize this mathematically. And it shows sort of what happens, that as the density is increased, the sound velocity squared increases. And typically at a few times nuclear matter densities, 3 to 4 times nuclear matter densities, it's already gotten up to scale which is of order, you know, a third, and presumably it's even exceeded that. That is really a remarkable empirical fact. Okay, it just is totally mind-blowing, and that's also tied into these suggestions that there is a very rapid change in the degrees of freedom and a narrow range of densities. One should understand where the sound velocity comes from. If you take dPdE for a system and you just use thermodynamic identities, you can calculate that the sound velocity squared is the baryon density for a purely baryonic gas. I'm not going to, one can consider a gas, well, okay, one species of a Fermi gas. The sound velocity squared is NB over mu B dNB d mu B. And you can see what this means. Okay, that's how the sound velocity behaves. You can convert that into a relationship for the typical change in the chemical potential over mu B times the typical change in the baryon density over NB by just replacing the D's by delta and doing some simple multiplication. And then you find this relationship, and this is quite remarkable also, because you see delta NB over NB is of order 1, B sound squared is of order 1, therefore delta mu B over mu B is of order 1. But ordinarily in a nucleon gas, mu B includes the nucleon mass, and then what you say is a change in chemical potential is associated with the changes in kinetic energies. And so you would expect expect this for a non-relativistic gas to be of order delta mu b over mu b to be of order 1 over nc squared, I guess, okay? It's very small. But on the other hand, this relationship tells you it's of order 1. That says the typical Fermi energies in this gas have changed by the order of the nucleon mass. And that's remarkable also, that the typical energy scale for the nucleons is the order of nucleon masses. That's not so unexpected, because the relativistic sound velocity should have relativistic degrees of freedom. But I find it all of this is totally mind blowing to me. Okay, so how can the density stay fixed if the Fermi momentum goes up? Well, this is a problem you have to solve, because the typical density scale is not changing very much, but the Fermi momentum is changing by a big amount. Well, imagine putting the nucleons on a shell of varying thickness as the density increases. Then the baryon density has to come in the form of new degrees of freedom quarks. So what I'm doing is I'm going back. Let's see if I can shift this. I'm going back to this picture where the nucleons sit on the Fermi surface and the quarks sit in this Fermi sphere, okay? And what I'm trying to do, what I want to argue is that if you make the thickness of the shell where the nucleons sit get thinner as the density goes higher, you can make the density of baryons in that shell be a constant, say some saturation density, okay? And then the density that I add into the Fermi sphere quarks goes up by some reasonably decent scale, okay? But you see, what can happen is if I'm making the density on that surface be small, the point is that the Fermi momentum of the quarks is going to be of order 1 over nc times the Fermi momentum of the nucleons. So if I take the Fermi momentum of the quarks and I get them up to the scale of order lambda QCD, so that I have a density of order lambda QCD of quarks inside that Fermi sphere, then the nucleon Fermi momentum has gone up by a relativistic amount, by the order of its mass. And you might have said, oh, that's horrible, because if I make the Fermi momentum be of order, several times the nucleon mass, the density is really high, because the density goes like the Fermi momentum cubed. But I can control the density in the nucleons by making that shell get thinner and thinner as the density goes up, okay? And the density in the quarks isn't very high, because it's of order 1 over nc times the typical Fermi momentum at the Fermi surface. So I can have a region where the Fermi energy of the nucleons can get into a relativistic region where I controlled the density and kept it relatively mild, okay? That's really remarkable that you can do that you can have a region where you increase in the density by the order of the QCD scale, yet at the same time, the Fermi momentum of the nucleons on the shell are become relativistic, but the density inside that shell is non-relativistic. Okay, you can see this in a variety of relationships, how this can happen. If you calculate the baryon density in terms of Fermi momentums of nucleons, you get a relationship which has K Fermi cubed of the nucleons cubed. If you do it in terms of quarks, you get K Fermi momentums of the quark cubed. If it was the density of quarks, it'd be an NC there, but quarks carry baryon number of 1 or 1 over NC. So the baryon density of quarks goes like the Fermi momentum of the quarks cubed. You see, the problem with this relationship is that if you have a constituent quark model where the nucleon mass is NC times the quark mass, the quark Fermi momentum and the nucleon Fermi momentum are related by a factor of NC. So, that means if you make a transition between quarks and nucleons and the density is roughly fixed, okay, then it's really something very violent happens, because the quark Fermi momentum goes toward a lambda QCD, and this relationship between nucleon and quark Fermi momentum means that the nucleon Fermi momentum becomes of order the nucleon mass. And that's what this shell allows you to do. It allows you to make this transition, okay, where the density can stay roughly fixed, but you can make this rapid change in the typical scale of Fermi momentum. You can also see how this happens, what happens with the energy density. The energy density is of baryons is of order mn lambda q QCD, which is order nc lambda to the fourth QCD. The energy density of quarks is lambda QCD times the number of quarks, okay? And the number of quarks is NC times the baryon number of quarks. So this transition not only happens at fixed baryon density, but fixed energy density also. So the what this proves is when you make a transition between quark degrees of freedom and nucleon degrees of freedom, the change in the energy density is of order 1. On the other hand, the pressure makes a big jump, because the pressure is Kf over mb for the energy density of nucleons. For quarks, it's the order of the energy density of quarks, which is the order of n. And so you see there's a big jump in the pressure. Okay, let's see. Did I skip something there? So now you're forced into a question, and the question is, how can you construct a theory which has both nucleon and quark degrees of freedom? This is an amusing problem here, and it's a problem which we have had and for a long time. We ordinarily kind of ignore it. We say, well, we can have quarks and nucleons together, but in a Fermi gas, that's a real problem. Because if you have a Fermi gas of quarks, where all of the states of quarks are completely filled, nucleons are made of quarks. So they're blocked by having that completely occupied state of quarks. So if you have nucleons, you have to remember that they're composed of quarks, and that the nucleons cannot exist in the region where there are quarks. And this is an old problem in theoretical physics, where you start with a theory which has too many degrees of freedom, and you have to cancel out some of those degrees of freedom. You studied this when you learned about QCD and non-abelian gauge theories, where you had a vector degrees of freedom and some Feynman gauge or Landau gauge, and it had too many degrees of freedom. And you introduced ghosts into the problem to cancel off the degrees of freedom of the unphysical degrees of freedom of the vector particles. You can do this here too. You can imagine a theory where you have nucleons, a theory where you have quarks, and to make sure that the quarks, that the nucleons don't exist where the quarks exist, you can introduce ghosts into the problem. And what the ghosts do is they'll cancel the degrees of freedom of nucleons in the region where the quarks sit. Okay, and to do that, you have to have identical interactions between nucleons and the ghost fields, et cetera, et cetera. And why do you do this? You do this so that you can generate a field theoretical mechanism, field theoretical description of the matter. To do this, it's clear that the ghost chemical potential is there only to cancel the nucleons where the quarks exist. So the ghost chemical potential is a function of the quark chemical potential. It's not an independent parameter. If you did this in some mean field model, you would know what you do. If it's just in the quark parton model, you'd say the quark chemical potential is equal to N, the gluon chemical potential is NC times the quark chemical potential, because that's where the top of the quark Fermi C exists, and that should be where the ghosts begin to cancel out the nucleon degrees of freedom. You can also do this in a mean field theory in the additive quark parton model, because what the mean field theory does is it shifts the energies of the nucleons by a constant potential, but then the chemical potential of the nucleons has that subtracted from it. And so the chemical potential of ghosts minus the mean field energy is equal to NC times mu quark. More generally, you can do that also because you expect that the phase space density of ghosts at the Fermi surface is NC cubed times the phase space density of quarks. And at first this might confuse you because, oh, how can that be? I think of nucleons made of quarks, and those nucleons which are made of quarks, I make NC quarks to make a nucleon, so shouldn't the coefficient be 1? And that's not true. And the reason why it's not true is because if you have nucleons made of NC quarks, you would have a Fermi, NC quarks would be 2 pi j NC over L. And then if you added NC quarks, which had a momentum which is shifted by j plus 1, those quarks of identical momentum would be 2 pi times j plus 1 times NC over L. And that would exclude nucleon states which had momentum between 2 pi j NC and 2 pi j plus 1 NC over L. It misses all the states of 2 pi j NC plus k over L, where k is between 1 and NC. And it's actually easy to understand what's happening is the nucleons which have these intermediate momentum where k is not equal to 0, they're made by quarks which have some momentum which is 2 pi j over L, but then you have k quarks which have some momentum which is shifted by 1 unit, so that the nucleons in these intermediate configurations are not blocked by states of quarks, all of which have the same momentum. Some of the quarks have a little bit different momentum, but nevertheless, they are still blocked. And so this is sort of almost a very natural relationship, which will determine the relationship between the ghost chemical potential and the quark chemical potentials. Okay, well, you can write down a theory like this. The theory is relatively simple to write down. And I did this Ki-Song and Diana and Saul. Basically, you write a theory with nucleons, a theory with ghosts, and a theory with quarks. And the ghosts are basically degrees of freedom which solve the Dirac equation, but they have both statistics. And their effect is to just cancel out the degrees of freedom in the intermediate range of, in the region of densities where the quarks are important. So it's very simple to write down such a theory. And then you have a relationship between mu b, mu g, and mu q. So that's determined. But if you look at that equation, there's still a degree of freedom for nucleons, a degree of freedom for quarks. So there are two parameters in the problem. What do they characterize? One parameter should control the total baryon number, and another parameter should control the density of quarks. Well, if you have an energy density functional, which is the functional of the nucleon density, the ghost density, and the quark density, then you can minimize this, holding the energy density at fixed baryon density to be fixed. Okay, that is fixing the basically the baryon chemical potential, and then varying it with respect to the quark density with the constraint that d rho g d rho q is NC cubed, and that's sufficient to determine the quark densities. So in fact, there is a well-defined theory you can write down as a field theory to describe this. Okay, but in general, that theory is of course not so easy to solve, because you will eventually have to put in interactions. You can play games. You can take a mean field theory, for example, where you add a mean field potential for the nucleons and nothing for the quarks, and then basically the nucleons and ghosts are 3 degrees of freedom up to the nucleon, up to the mean field, and the quarks are treated as 3 degrees of freedom. It turns out if you do that and you make the nucleon masses the same as the as NC times the constituent quark masses, there will only be a discontinuous change between a gas of all free quarks and all free nucleons. But of course, that story is not really right, because the quark masses are really, the constituent quark mass is really not the nucleon mass over NC. It's some average mass of excited nucleon states, deltas, and whatever, divided by NC. And so when you put that into the problem, you do split things apart, and you do find a quarkyonic phase. In mean field theory, it turns out, and this is all work in progress, which should be out, I would assume, over the next few months. If you just add in a pure mean field and you treat the quarks and gluons and nucleons as free particles, except for that mean field, then you will find there will be a first order transition. And beyond that first order transition, there is quarkyonic matter. That's a little unpleasant because the neutron star data should have a weak first order transition. These are generically pretty strong. You can also put in the interactions, the mean field interaction, in a different way. That's something I developed with Kisong and Diana and Saul. And that's where the mean field modifies the kinetic energy terms for the nucleons. That happens if you have an excluded volume model, because in an excluded volume model, the hard cores of nucleons repel nucleons from the region where the cores are at. And so the effective volume in which the nucleons propagate is given by a reduced volume, so their kinetic energy shift. In that theory, you actually find that you can get a second order transition if you modify the dispersion relation between quarks and the density, stall density. Simplest possible modification is you make the quark Fermi energy the mass of the quarks plus a rho quark over lambda squared. That works, and there's a nice second order transition. I should say the story of making models of how quarkyonic matter occurs and understanding how interactions do that. These are all attempts not to really construct a realistic model of quarkyonic matter, which describes neutron stars. They're basically understand what's going on, because and the progress on this is very, very hard, because when you don't understand something, you don't understand it. And so you try various things and you make various efforts, and eventually you make some progress. But we think we understand some basic outlines of how this goes. I should say the basic idea we're trying to implement is that when you have this shell of nucleons, okay, the nucleons have repelling hardcore interactions. That causes the density of the nucleons to saturate, and then the sea of quarks, or fully full nucleon states, if you like, fully full states which have the quark states completely filled, begins to appear. And I think generically that's probably what really goes on, but to understand how to generate a correct theory, a phenomenologically correct theory, which has all of the ingredients added in correctly, it's a little harder. I should say also that my picture of what goes on deep inside my soul, as opposed to what I can calculate, and oftentimes I operate from deep inside my soul because I know of no other way of doing science. What I think really goes on is that this transition between all nucleon matter and quarkyonic matter is probably not some kind of phase transition. It probably happens pretty smoothly and continuously. And then what happens as you crank up the density, the degrees of freedom of what you're calling the Fermi surface stay in the degrees of freedom of nucleons. But then as you go deeper and deeper into the Fermi sea, it becomes states which are full of nucleon degrees of freedom, which then as you increase the density, those quark states are realized and thought of more in terms of quark degrees of freedom rather than in terms of nucleon degrees of freedom. So my thinking about this is that the transition to quarkyonic matter is probably more continuous than these models would have us believe. But that said, I think we owe it to ourselves to have a dynamical understanding of how quarkyonic matter might occur. Now, in the last few minutes, I should mention some ideas about what this might mean phenomenologically. With RHIC and Sorensen and Volker, we were asking a question also experimentally: how do you realize this? And if the sound velocity squared really rises very quickly, one should be able to see it for moments. And we were able to construct a combination of moments of baryon number fluctuations, which at low density should reflect this rapid increase in the sound velocity squared. That's very important, because if you can see this occurring in experiment, then one can get some information which is unique at different values of baryon and isospin density, and also just to confirm what happens, the inferences from neutron stars are really true because you can see it in a laboratory. That said, there's another issue which I think is also very important. How does one really formulate a good transport theory where you take two nuclei which are made of nuclear matter at relatively low, at intermediate energies, and you scatter them off one another, and somehow you make a high temperature distribution of quarkyonic matter? Well, one question you have to ask is, how do you construct a theory of quarkyonic matter at high temperatures? What does it really look like? That some work was done by that on that by Shimoy Sen, and it's, I think it's a very, very interesting question. So I'll leave it at that. I've had my share of time to talk. What I should do is, should I turn this off from the share so I can see people now, Kenji? Kenji?
Maybe if you are being asked questions to go back to certain slides, it would be good to still have them up.
Okay, good. What I'll do is I'll put this, okay. If I put it, let's see, can I see people here? Yeah, I can see people now. Okay, good.
So you don't have a conclusion slide, or?
How can I draw conclusions? You know me, my conclusions will always be changed in a few weeks. You know?
Okay. So questions or discussions, or? So the audience seems to be very silent today. Okay. So Nu, please go ahead.
Hey, Larry, thank you for the nice talk. I have a simple question, which I always ask you. What would be the experimental consequences? You mentioned some fluctuation. Do you have any specific suggestion that?
Yeah, well, right. No, we're thinking about this problem, okay? And one thing we found were these moments analysis. One, you know, and that's that we've written that up with Volker, and that's interesting because there you can get basically the sound squared plus the logarithmic derivative of the sound velocity with respect to the logarithm of the density, and there is some information which is very suggestive by combining the RHIC data with the Hades data. If you look at this combination of moments, it goes along a nice line and changes very dramatically at the when Hades is there. Okay, now I don't know what, you know, it's too early to draw any kind of strong conclusions from it, but it is interesting that you can get information like that. But the thing which we really would like to do, and we're struggling to do, is try to construct a transport theory which builds these properties in. And transport theories, when you have these different degrees of freedom, it's kind of harder to understand. And it's also harder to understand how you build in things like mean field potential, scalar and vector potentials in the problem. One understands currently how to put a vector potential in, but I would like to see a model where you take two nuclei at intermediate energies, they scatter from one another, and then you can trace the evolution with the possibility of making quarkyonic matter in the later stages. Even that simple thing has not been done. Okay. And moreover, one doesn't understand. And when you do this, you of course will make matter at higher, it'll be excited matter, it'll have some temperature. Understanding how you handle meson degrees of freedom at the system of high temperatures is not easy either, because mesons are also made of quarks and they'll be Fermi blocked. And how do you build all of that into the problem? So, you know, this is in a very, very primitive state, and it's hard, but we're making some progress and we're interested in the problem. And I just don't, you know, hey, hang on, we'll make progress.
The star data on 3 GeV collisions, center of mass 3 GeV collisions are coming out, and the 3 papers already accepted by journals. And there we found the typical, let's say, typical signature of a partonic matter disappeared. We actually do not see almost any of them. And we also, the high moment measurement of 3 GeV also in referee's hand at the moment.
Well, the analysis which we made for the sound velocity squared does not depend upon whether or not there's you know, partonic or quark or nucleonic matter. It's a simple statement about the sound velocity squared. And if you can get some constraints on the sound velocity squared, those constraints will be true constraints, okay? And that's interesting in itself.
But that depends on the mu b, is that right? Or mu q in your language. Hmm? Has to be, right? Because yeah,
we're just simply doing a moment analysis.
Mm-hmm.
And it's related to the sound. The moment analysis, which we prove, gives a relationship between a combination of moments and the sound velocity squared, okay? And its derivative with respect to n. But those things are empirical things you want to know, okay? If you can get us constraint on the speed of increase, the sound velocity squared plus the sound velocity squared, and it's really a strong constraint, that's very, very interesting, because the neutron star data indicates that this is rising very rapidly. And then one needs to know what density one's talking about and hone it down and do real calculations to see, you know, what it's really reflective of, because our considerations are equilibrium considerations and your considerations are really the dynamics. So that has to be done too. But yeah, what can I say?
All right, thank you.
Okay, thank you. Okay, the next question by Jin Feng, please.
Hey, Jin Feng.
Hello, Larry. Yeah, nice to see you and hear your talk again. Well, thanks for nice talk, and I have some naive question. Can you hear me?
Yep, I can hear you. Good morning.
Okay. Yeah. Yeah, it's really good morning for you, of course. So I'm being naive. Let's say, of course, at the beginning of the talk, you emphasized that how rapid that you know speed of sound rise to a very high value. But you know, if I'm being naive, if I only think about a gas of hardcore particles, I can get whatever I want essentially. You know, the density where it starts to rise is essentially controlled by the scale of that hardcore size, or how large it can shoot up depends on the strength of that hardcore potential. So naively, you would say going up is not terribly surprising. I mean, in principle, one could couple that with some strong nuclear hardcore. So my naive understanding that what quarkyonic matter does really well to sort of bring that back down to a quark matter in a smooth way. So that's sort of just my naive understanding, but maybe you can comment on that.
I agree with you completely, but then I'm turning, if there's a maximum there, okay, then what I'm saying something is very interesting associated with that maximum, because that tells you the change in degrees of freedom between nucleon degrees of freedom and quark degrees of freedom, okay? And that's just an interesting thing to know, okay?
I see.
So I don't disagree with that. I mean, what the quarkyonic matter does is it softens it. And intuitively, that's quite plausible. because the cores of nucleons are beginning to overlap, which is what happens when the sound velocity squared becomes significant in a hard core model. You would expect the quark degrees of freedom to become important. But then we have this problem in the relationship between the quark degrees of freedom and the nucleon degrees of freedom, and it's this factor of NC. And you think that's a small factor, but in energy densities, it's NC cubed, so that's a factor of 30. So to make that transition occur, you have to have something fairly dramatic happen to the underlying degrees of freedom. But yes, it's driven by that observation that the cores are what are causing it to rise up. The quark degrees of freedom come in. The quark degrees of freedom may participate in the rise too. Okay, there's certainly duality, and it depends on how extreme you want to be. Do you want to have it? You could imagine the nucleon degrees of freedom all the way up. You could imagine part of the way up. What's the truth? You need to understand, but certainly something very dramatic is happening there, and it's that observation. So we don't disagree.
Yeah, I completely agree. So you're saying basically that the observation from neutron star and so on that will help us understand if going up and turning back of that speed of sound, which provides the essential information about the quark degree of freedom.
I would say it's even interesting, even if it doesn't have a maximum, if it just goes up. And
but there is, of course, always the upper limit of speed of light.
Yeah, but
you haven't turned back.
Yeah, but can you imagine a conformal field theory for just nucleon degrees of freedom at those densities?
Okay, so maybe I make one more sentence remark. So basically, you're saying that in the temperature direction, you go through the confinement, the deconfinement to go from hadron to quark, and in the density direction, you're saying that instead of doing that, you are turning smoothly from a quark nucleon into quarkyonic, and eventually maybe totally quark.
Yeah, that's right. There's an interpolation.
Yeah, okay. Yeah. Thank you. Yeah.
But it's a big region in chemical potential. It's not a small region. It's
sure.
Or when you think interpolating region, you think it just kind of is some short region where you do an interpolation. Here, the region is huge, where in terms of chemical potentials, where you make that transition.
Okay. Thank you.
I think that the Jinfen has a very good point. So the common folklore is that the interacting nuclear matter can be stiff enough to have a big speed, the speed of sound, but the transition to a quark matter, usually the existence of a quark matter makes the EOS softer, and so so that is a common folklore. But so your quarkyonic scenario is something more non-trivial, very non-trivial. That's very interesting. Okay,
yeah, because
so
quark matter is always less. Sound velocity squared is always less than a third. So doing that interpolation, that's right. Yeah, I agree, Kenji.
Okay,
right.
So let's go to the next question by Chemin. Chemin, please.
Oh, Larry.
Hey, Ming, nice to see you.
Yes, very glad to hear your nice talk. My question is back to Lucy's question. He said, is any way to see the effect of quarkyonic matter in heavy-ion collisions? And I remember some time ago people talk about, because you introduced a new phase between the normal nuclear matter phase and the fully deconfined quark matter phase in heavy-ion collision at the low energy baryon-rich matters. So we have learned a lot in the past from dilepton productions, right? Like Rolf did a lot, many other people, Charles Gale did a lot. They can tell how those dileptons come from hadronic phase, those dileptons from the platonic phase. So if there's a long period duration of quarkyonic phase during the heavy-ion collisions, one should have a different source of dilepton come from quark meson production of dileptons, which is not including in all the old studies, even including that entirely from hadronic phase or entirely from the quark method, but nothing from meson quark interactions. So if I look, I don't know which invariant masses that those dileptons will dominate. If they do some experimentation with dileptons and they use the old modeling, if they see some extra enhancement in some invariant mass, maybe indicate something interesting going on. So that is I don't know, that's maybe a long way to go.
Yeah, it's a very, very, very interesting question you're asking. Okay, let's assume you were in equilibrium matter and you had high temperature, high density and lowish temperature. What are the degrees of freedom? The degrees of freedom are nucleons near the Fermi surface and quarks inside the Fermi sphere deep inside. But the meson degrees of freedom are presumably responsible for a lot of the production of photons. Okay, and so then the question becomes, how do you really calculate that? And right now we don't really have, I think, a complete theory of what happens at even low temperature and high density. And the problem there you have is that the mesons are at least partially blocked by the Fermi sea of quarks. How do you build that in? How do you really do that calculation correctly? I think it can be done, but it hasn't been done. And
there's a long way to go.
There's a long way to go. You know, you looked into a dark forest, see there's a path that goes a little bit away. You walk in, you hear wolves howling by the side, scared. The standard thing. But I think there's some things to discover there, which I think are interesting. And what you're suggesting is a very, very interesting problem, which goes to a fundamental question of how do you write down a theory for this at finite temperature, which is a consistent field theory.
Yeah, but my point is that for those people doing model.
I lost him.
Chairman, you are muted. Chairman, you are muted.
You're muted. So please unmute yourself.
Oh, yes. But my point is, right, before one can calculate, one can still, hopefully the data come out from others, maybe some other experiments, and the people doing dilepton calculation, they should predict. And any deviation, if they can, in the old days, they can fit the data perfect. Most of them, if I remember transport model calculations, they can fit the data from RHIC, and data from RHIC, can fit the data from GSI. Now, if you go to a region expected as a part of Quarkyonic methods, they should make a prediction without that phasor methods. Then if you see if they found deviation from the measurements that into something interesting, may or may not be due to Quarkyonic methods. So that's my point.
Yeah, it's a good point. I agree.
Thank you, Larry.
Okay, so is there any other? Yeah, in fact, I have a bunch of questions, and one of them is related to Chemin's point. Larry talked about many things about the confinement and the sound of the speed of sound, but what about chiral symmetry? The realization of chiral symmetry breaking in quarkyonic matter and the hadronic matter, that is very different, right? And so in such a state of the mixture of quarkyonic matter and the baryonic matter, what is actually the the state of the chiral symmetry breaking?
Well, what I can tell you what the state of knowledge is, and this was done some time ago by Toro Kojo. And what Toro did was he wrote down, I think this was with Alex Velik too, at least in part. But what Toro did was he wrote down a Lagrangian which described the Fermi surface of nucleons and mesons in quarkyonic matter. And he found that surface broke into patch structures. And in fact, it was very, very peculiar. In a large NC limit, there were a large number of different inhomogeneous phases which let you interpolate between the homogeneous phase of chiral symmetry breaking at low density and a phase which has basically a ZN symmetry at higher values of density. And this was also found in Nambu-Jean-Lacinier models. When they went back and looked at NJO models, it looked like there was a continuous transition between hadron phase and quark matter phase at a density a few times, well, at a density close to the density at which baryons first occur. But then they looked at it more carefully with allowing for inhomogeneous phases. This was largely the Darmstadt group. And they found that, in fact, there were various inhomogeneous phases there. And you could have a region which looks like this Quarkyonic island region. Remember, I did this happy island thing as a joke for you once. But in this happy island, there are many, many different ways of realizing the chiral symmetry breaking.
Yeah, in fact, Larry, so my question is more specific. I mean, I know that scenario. I mean, the Fermi surface is patched by several regions, and then that's how you get such inhomogeneous region. But in your picture, not really the Fermi surface area, but you talked about the thickness of the Fermi surface or some Quarkyonic region, right? And so as a function of such the thickness, what happens? What changes in the realization of such inhomogeneous state?
I don't know. Okay, I simply don't know. It's a very, very, very interesting question, right? You know, if you know, one of the problems about claiming you know everything is first, it's never true. And then the second problem is that there's nothing to do. But it's a good question.
Okay. Yeah, in fact, you know, the chiral symmetry realization is very sensitive to the dilepton measurement, and so this should be a very interesting from the point of view of experimental efforts. Okay, so is there any other question or discussions or some? So anything from the audience? So this is a Q&A session, and so please don't hesitate asking any question.
I'll throw out just a remark. This is Scott Pratt. Hi Larry, how are you doing?
Scott, how you doing?
See you in a week, I guess. And anyway, and that is that if I'm sitting here looking at actually it's a book about metal insulator transitions, and oh my God, what a rich variety of possibilities you'll see for that. And then in our system, we also have the chiral symmetry thrown in. And so theoretically, I think this is, you know, there's just many possibilities one could have if one just thinks about theoretical possibilities. And for experimental information about the speed of sound, I think something that's really interesting, a result that's come out of mainly the beam energy scan range, is that if you look for the softest point, which means like they're mainly through like HBT measurements, you would expect that if you went from, say, 5 GeV collisions where you maybe you have the maximum density to 20 GeV collisions where it turns out that it's softest, you'd be surprised by that, because you would think that at 20 GeV for roughly the same energy density, you have a lot fewer baryons and you know, and more pions, and you would think it would be softer because you don't have to move all those heavy baryons which don't contribute to much of the pressure. But the result is that the softest point is, you know, in energy density well above where you might think it would be. And one possibility is that as you go down in energy in the collider down to the 5 GeV region or so, the lower beam energy scan regions, that higher, the baryon density is higher, and the repulsive energy between baryons is just really, you know, extremely significant. And it would be interesting to do, you know, to see more detailed, careful modeling of this, effectively looking at the speed of sound all through the beam energy scan region.
Okay, thank you very much. So is there any comment from Larry?
No, I agree. Sounds
Okay.
you do.
Yeah.
Okay, so there's actually a question from Chung Wang. So please.
Hi, Larry. Thank
Hi.
you for this nice talk. Can you explain a little bit why do you introduce the ghost field? So I didn't get the point.
Oh, okay. So what the problem you have is if you write down a Lagrangian with both nucleons and quarks, okay, the problem is that nucleons are made of quarks. So you can't have them both filling up all of phase space, because where quarks are sitting, the nucleons can't, because there's a Fermi exclusion principle. So what you do is you introduce a ghost field into the problem to cancel the degrees of freedom of the nucleons where the quarks sit, okay? And so what does a ghost degree of freedom does? Well, suppose you have a determinant, which you get from doing a path integral, okay? If you have a determinant for fermions, it's the determinant upstairs, okay? But then if you have a ghost field, you want to cancel part of that determinant, so you have to have a determinant downstairs. So to do that, you have to have a field which solves the Dirac equation. So it looks like an ordinary nucleon, but it has to be a boson, because bosons, when you do bosonic integrals, you get a determinant downstairs. So what happens is the determinant upstairs from the nucleons is canceled by the ghost determinant downstairs, which arises from having the boson degree of freedom satisfy the Dirac equation, but satisfy Bose statistics. So the ghosts are basically bosons which solve the Dirac equation, but they're only there in the problem to cancel out degrees of freedom where they shouldn't be. So you should never think of the ghost as being a real degree of freedom. It's only there to cancel out the degrees of freedom of nucleons where the nucleons shouldn't be. And so this opens up a new way of thinking about effective field theories. Ordinarily, people write down effective field theories for nucleons, or they write down effective field theories for quarks. This, at least in this restricted example of finite density, lets you write down a field theory which has both. So I think that is a theoretical development, independent of all the rest of this stuff, is kind of interesting.
Well,
thank you.
Yeah, but the question is, what is actually the advantage of such a formulation instead of excluding some phase space by hand?
Well, you can do it by hand, but sometimes you don't know how to do that. And with the field theory, you can also calculate interactions to all orders and have this systematically accounted for.
But how do you know the interaction involving the ghosts?
The ghost interactions have to be identical to the nucleons because they're ghosts.
Well, but you should think about the ghost nucleon interaction. How do you fix it?
Well, the ghost nucleon if it's through mesons, there's no direct interaction between ghosts and nucleons, no contact interaction. So if it comes through mesons, the interaction of ghosts with mesons is the same as interaction of nucleons with mesons.
Okay.
It solves some of these problems. It's not a trivial. I agree. You could do all of this by hand, and basically ghosts are just advanced accounting and getting your master's of physics education, right? Master's of physics, master's degree in physics or something, like masters of business and accounting and stuff like that. It's a way of counting things, but it's a very powerful way of doing that. You could say that in Yang-Mills. You don't have to introduce Faddeev-Popov ghosts. You could always cut things out of integrals, but Faddeev-Popov ghosts are incredibly useful for actually calculating things.
Yeah, sure. So as I already pointed out, so this formulation is very similar to the chiral effective theory to emulate the quenched approximation.
Okay. Did they do ghosts there?
Yes, they have the ghost to kill the.
I didn't know that. Could you send me a reference to that, Kenshi? I
already sent you the reference.
You did? Okay, well, I forgot. I'm sorry. Okay.
Well, Kenji, send it again.
I didn't know it had ghosts in it. They really put in ghosts, huh? Okay, well, fine.
Okay, so
what happens when you get old and stupid, Kenji?
What?
Is what happens when I get old and stupid. What can I do?
Yeah, so okay, so is there any question or comments or So there are interesting discussions already, but if you have anything, no? Okay, so probably this is the time to close the discussion. So Ulrich, what should I do?
Clap to thank Larry.
Okay.
Very,
Thank you.
Very stimulating talk.
Yes, stimulating, very stimulating. Yeah.
And then we
Okay.
can close the seminar.
Yeah, Kenji, whenever somebody says it's very stimulating, you got to be worried.